Okay, Calc. This is section 6.5, integration by substitution. All algebra stuff today, so no really graphs or drawing anything. I, Substitution is like one of my favorite things to teach. And I know I say that about a lot of things, but I really like substitution just because it pans out really beautifully. Integration, again, is finding the antiderivative, and let me kind of relate this to finding the derivative, okay? So this is antiderivative, okay? And substitution is what we use in scenarios that for derivative we would have used like the chain rule or the product rule or the quotient rule. So for derivative, we have 4 different rules that we can use. We can use the power rule, which is just the basic easy drop the exponent down in front, that type of thing. Or we have a product, or we have a quotient, or we have a chain. Okay, we have all 4 of those rules for derivative, but for antiderivative, we really only have been able to do stuff like the power rule, right? We can only do 1 over n plus 1 x to the n plus 1 to things that are really easy, like, you know, 3x squared, right? 3x squared, we would do 1 over n plus 1. That's kind of like a power rule type of thing. But what do we do when we have like something more complicated that we would have normally done the product rule, quotient rule, chain rule if we were doing the derivative, but what's the equivalent of that for antiderivative? And that's what substitution is used for, okay? So substitution is what you use when you have a composite function. And a composite function is a function that's composed inside of another one. Like you might have x plus 3, but it's stuck inside of square, right? So this is composed inside of that square, right? So that's a composite function. So you'll learn to recognize composite functions as we go through here and kind of see how the derivative of that composite function will show up in the rest of your equation. So I'm going to skip down to this guy, example 1, and then maybe we'll come up and talk about the table here for just a second. But when you're doing substitution, what's going to happen is your composite function, or the function that's stuck inside of something else, you're going to notice that the derivative of that thing will end up showing up in the rest of your substitution part. Okay, so for example, the composite part, or the part that's stuck inside of something else, is this x squared plus 1. He is trapped inside of the square, right? Okay. And x squared plus 1, if I take the derivative, not the antiderivative, the derivative of that is 2x, and the 1 just drops off. Well, notice that 2x actually shows up right there, okay? So this ends up coming out really nicely, and everything just basically cancels out when you substitute, and it just is beautiful, okay? Same thing here. The thing that's stuck inside is going to be that 5x plus 1, and the derivative of 5x plus 1 is just going to be 5, which shows up right here, okay? So that's something that you will notice. You'll notice that you'll have a g of x and you'll have a g prime of x going on inside of your function here. So you have a g of x stuck inside of some function, right? G of x is stuck inside of f of x, but then g prime, or the derivative of that g of x, showed up somewhere else in the equation, okay? So let's go down to one of our first examples, and I want to show you how substitution works. So what you're going to do is you're always going to change your variable because it makes it way easier to deal with. So we always change the variable when we're doing substitution to u and du, okay? Rather than x and dx, okay? We're going to switch from x and dx to u and du, and I'm going to show you what that process looks like, okay? So if I'm doing this function right here, okay, I need to label out what I'm going to designate u to be, all right? And u is going to be the composite function. Composite function, okay? This is the function that's stuck inside of something else, right? So 2x minus 1 is stuck inside of the square root, okay? So I'm going to designate that as u, and then he's just basically gone, right? Okay, now du, or the derivative of u, okay, the derivative of u, the derivative of this guy, 2x minus 1, is just going to be 2. And then I write that as dx so that I know that I'm taking the derivative with respect to x, okay? So the derivative of u the derivative of this guy is 2. I take the derivative on this side, which is 2 dx. Okay, we write that just like that. Okay. And then what I do is I start to substitute stuff in. Okay, so I have my integral symbol, so I'm just going to rewrite this guy. Here's my integral symbol. I'm going to rewrite, I have a square root, and 2x minus 1 has become u. Okay, so basically I've gotten rid of this thing, I've rewritten him. Okay, I've gotten rid of my square root, I've rewritten my square root. 2x minus 1 I've rewritten as u, and then I need to rewrite dx. Okay, I need to rewrite that dx in there. Okay, but dx I don't have solved for by himself here. Okay, I have 2 dx, but I want just dx, so what I can do is I can divide the 2 over, and I can rewrite dx as du divided by 2, or 1/2 du. Okay, so when I rewrite and when I substitute in my dx, I'm going to put in 1/2 du. Okay, so I'm going to put du at the end here, and then I'm going to put my 1/2 in there, which is going to go, I usually put my 1/2 out in front, like that. Okay, all right, so basically I just took this piece by piece, and using my u and du, I've plugged the equivalent form in, and now I have changed the variable, okay, to u's and du's. Okay, now from here, what I'm going to do is we had a rule before that said that this 1/2 really does nothing, and I can lump that 1/2 out in front. So I'm going to put the 1/2 out here, and basically that allows him to just chill out while I take the antiderivative, and he doesn't affect anything. And so what I'm going to do is I have 1/2 out in front. I have my integral, and I'm going to write this as u to the 1/2 power du. And then I need to take the antiderivative of this guy right here. Okay, so antiderivative of u to the 1/2 power, this gets kind of messy. It's 1 over n plus 1. Yeah, n is that 1/2. So 1/2 plus 1, u to the 1/2 plus 1. Okay, that's what my antiderivative of u to the 1/2 is going to be. All right, 1/2 plus 1 is 3/2. And if I flip that around, 1 divided by 3/2 is 2/3. And this is going to be u to the 1/2 plus 1 is 3/2 again. Okay, all right, so think about taking the derivative of this guy. If I take the 3/2 power and multiply by 2/3, that gets rid of it, and this is u to the 1/2 power if I subtract from that exponent. So I get back to the original. So 2/3 u to the 3/2 power is going to go in here for this whole thing. So I have 1/2 times 2/3 u to the 3/2 power. Don't forget your plus c on the end, because we're not plugging in numbers here, so we need to have that plus c on the end. And then I'm just going to simplify. So 1/2 times 2/3, those 2's can cross out. So 1/3 u to the 3/2 power plus c. And then the last thing that I do is I switch my variables back. So I didn't want u to begin with, I wanted x, but we switched it to u to make it easier, okay? So this u is going to be replaced, no, I shouldn't do that. This u is going to get replaced, and he's going to be replaced with what we designated as u to start with, okay? We designated u to be 2x minus 1. So I'm going to do that. 2x minus 1 goes back through here, and this is going to be my antiderivative, okay? So kind of a messy process, but we're getting there. So, all right, now this next one, same process again. We need to decide what we're going to label as u and du. I'm going to do this, okay? What we're going to label as u and du. So the stuff that's stuck on the inside is x squared minus 1. And then we need to take the derivative of that. So the derivative of u is du, and the derivative of x squared minus 1 is 2x dx, right? The derivative of x squared is 2x. The 1's going to go away, and the dx is going to stay on the end because that just says I'm taking the derivative with respect to x, okay? So that's what he will look like, and then I just start to plug stuff in, okay? So I'm going to rewrite my integral, okay? He's going to get replaced over here, okay? My square root, I'll go ahead and rewrite my square root, okay? x squared minus 1. I'm going to replace him with u. And then x and dx. I need something to replace x and dx. Okay, well I have x and dx right here in my in my derivative. Okay, but I need to get rid of that 2. So just kind of how we did up above here, I'm going to divide the 2 over. So I can write x dx as 1/2 du. Okay, so the x here and the dx here, x dx can be replaced with du and 1/2. Okay, and that's what he would look like, right? Okay, so kind of a similar process to what we had before. Like, how did that happen? 1/2 the square root of u du is exactly the same thing as what I have here. So what I'm going to do, I'm going to kind of cheat. I'm going to go down to this part right here. I know that the antiderivative of 1/2 the square root of u du is 1/3 u to the 3/2 power plus c, right? Because it's going to have the same antiderivative all the way through there, right? And then all I need to do is replace my u back with an x again, right? Okay, so 1/3 u to the 3/2 power plus c. Okay, and that's what he's going to look like. And then u was actually, we designated him to be x squared minus 1. So that's what he will end up looking like. And there we have our antiderivative. Okay, all right, I'm going to do one more, but I'm going to go back up to this top part here. Let's do this example, this first one, number 1. And let's go ahead and figure out what our u and du is. Okay, I'm not going to do the second example. I'm just going to do this first example so you can write in this whole space right here. Okay, so let's figure out what u is and let's figure out what du is. Okay, all right, u is going to be the stuff that's stuck on the inside of something else. So he's stuck inside of the square. I'm going to write him as x squared plus 1. That's the part that's stuck on the inside. Okay, and then the derivative of that is just 2x. The 1's going to go away. And we put a dx on the end there. So this notes that I'm taking the derivative of the right side with respect to x. I take the derivative of u with respect to u, and that becomes du. Okay. And so we have this going on here, and now we're going to start to substitute in. So I cross off as I substitute. So I write my integral symbol, integral. Okay. X squared plus 1 is going to go away. He is replaced with u, and that will be u squared, because x squared plus 1 squared will now become u squared. Okay, and then in this one's kind of nice because 2x dx, I need to replace him also. 2x dx, I don't have to divide anything over to the other side. I can just replace him with du. So 2x dx is exactly the same thing as what du is. So I'm going to do du here. Okay. All right, so substitution is a little bit tricky just because you're taking the derivative here. This is derivative. And then now we have to take the antiderivative. Okay, so you're doing both in the same problem. So it does get kind of messy. We need to take the antiderivative of u squared. Okay, so that's the 1 over n plus 1, x to the n plus 1. 1 over n is 2. So I have 2 plus 1, u to the 2 plus 1 power. Okay, and then I'm going to put plus c on the end there so I don't forget it. Okay, so this is going to end up being 1/3 u to the 3rd power plus c. There's my antiderivative. I'm almost done, except now I have to replace my u back with whatever I designated him to be. Okay, so now that u needs to become 1/3 u cubed plus c, and u we said was, blah, 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 where's my u? U is x squared plus 1. Okay, I feel like this one was an easier one than the other ones just because we were taking the antiderivative of u squared rather than taking the antiderivative of u to the 1/2 power, which can kind of get messy. Okay, but same process. I've given you kind of 3 examples of what that will look like. That is the integration by substitution, or the general form. Each one of these that we just did, these were all indefinite integrals. Okay, so we need to write that down. Indefinite integrals. because they did not have any limits, okay? On the back side, let me go up to the top here, I'm completely off the page. They did not have any limits of integration, okay? They did not have any numbers for us to plug in, like we did in section 6.4. That's what we're going to do on the back side of this sheet when we plug in like 0 and 1 and what we're going to do with those, okay? So I'm going to save that for the next video. These were all indefinite integrals. Hopefully you kind of get the idea of what that's going to look like. Let me know if you don't, if that's kind of a struggle. But the more you do these, the easier they end up being, okay?